Okay, so the last thing I want to talk about under this topic of catalysis is actually we've been focusing on the molecular level when we talk about catalysis, and now I want to bring that back up to the reactor level. So we think about a catalytic reactor. So the reactor level looks something like this, and I'm going to use a tubular reactor as an example. So, imagine that we could peer inside this thing. So this is maybe this is painted, and so it's painted, and so we've scrubbed off a portion of the paint so that we could view inside. And if we did that, we would see all these catalyst pellets, and we've said we can think of catalyst pellets as being spheres. They're certainly not always spheres, but for our purposes, it's a nice model. So now let's zoom in on one of these pellets. So pellet level. So the pellet is a sphere. And we said that the spheres are porous. So they've got lots of pores. The pores aren't really they're not given any sort of organization, right? So it's a porous material. We've used the example before, like a sponge, right? So it's not like it's a pore that goes straight through the material. It's got, bends and turns and curves, kind of almost randomly distributed, and that's intentional because the less organized it is, the more surface area that's going to create. So that's a good thing. So if we were to now zoom in, so we go from the reactor level to the pellet level, so now why don't we go to the pore level? So we zoom in to the pore level. If we were to look then, we would have this pore network. And like I said, this is kind of randomly defined. I guess in some cases people have probably engineered. In fact, people have engineered pore structures. So if you're looking at a catalyst where there's been an engineered pore structure, you might know something more about it than what I'm drawing here. But I'm basically just drawing kind of a random pore network. So then we said, okay, well, this is a pore. This is still probably large compared to the actual molecule. So let's zoom down to the pore surface. So we'll say catalyst level. So there we said, here's our pore. This is the bottom of the pore. The top of the pore may be even like way up here. Who knows? So this is our pore surface. And we said that we would probably have a supported material. So this is a catalyst support. And then we have our catalyst particle. So then we could zoom in even further. So to the molecular level. And that's what we showed in the more recent lecture. So here we have the catalyst surface. Notice that I drew this thing as flat. So here I have this particle that's got some curvature to it. Here I'm drawing this as flat because to the molecule is so small compared to that catalyst particle that it just sees the flat surface. It doesn't even know that this is curved. So we have, molecules here, and I'm just going to kind of draw a molecule. We have adsorption. We have surface reaction. We have desorption. So a lot of processes that we have to think about in catalysis. So let's look at this from the perspective of a gas molecule. So say from the perspective of a gas molecule. So at the reactor level, I have a collection of gas molecules. And they're all traveling through the reactor through convection. They're being drawn through the reactor by the flow rate. So if I go down to my pellet level, I have this pellet surface, and in fact, it's probably not curved either. I probably have, a molecule approaches that, and it just sees a flat surface. So I have some molecules are going to be trapped by this pellet, simply because it's in their way. Other molecules are going to flow past the pellet. So if I have, so this would be surface from molecule standpoint. Alternatively, I would have my pellet, and I have all these teeny tiny molecules, probably even smaller than that, that are kind of blowing into this thing. So some of the molecules will be trapped. Some of the molecules are going to be trapped, so these molecules here, maybe some over here. These molecules are examples of ones that are being trapped. Those maybe are approaching right here, and again to those molecules, since they're so small, despite that this is a sphere, it looks like a flat wall that they're running right into. So some are going to get trapped and some aren't. So some are going to continue flying by. So these ones, these ones are going to get trapped for sure. These ones, did not get trapped. So if we zoomed in here, so let's go back to this diagram. So look, if I'm a molecule that's gotten trapped, so we'll say the pellet surface, I'm going to draw one pore, and I'm not going to give it too much definition. So this is one pore. So I've got here one of these molecules that's been trapped by the pore surface. That molecule now needs to diffuse. So if we have my pore surface, the molecule needs to diffuse from the boundary layer. So if the molecule is trapped, it's entered the boundary layer. So we can say boundary layer. So we know that this boundary layer is actually a stagnant film that surrounds the pellet. So the only way for this molecule to get from the boundary layer, the top of the boundary layer, to the pellet surface is to diffuse. So the molecule, if it wants to react, or if it's going to react, it has to diffuse to the pore surface. So what's happening there, we have a molecule in the boundary layer. and it's going to diffuse to the pellet surface. Once it does that, it's going to have to diffuse into this pore. So we get kind of closer. We have this pore. So now I have a molecule that's gotten to the pore surface. To react, it has to diffuse into the pore. Once it diffuses into the pore, it has to diffuse throughout this channel. So I have these channels. The channels, of course, there's catalyst along here somewhere, so we can kind of draw where that is. And there's probably more than what I'm drawing. I'm just for illustrative purposes. So we have to diffuse until we find a catalyst. So it's got to diffuse to the catalyst. So we call this internal diffusion. And we call this external diffusion. And once the catalyst diffuses, it diffuses into the pellet, it finds a catalyst particle. It has to find a catalyst particle that's active. So if this particle is closer to the mouth of the pore, possibly it's become already covered up with catalytic species, so maybe this one isn't so active, so it's got to keep diffusing until it finds one. So it finds one, then it's got to react, which means now to react, it has to find enough energy to overcome all of the relevant activation barriers. So to do that, the molecule has to absorb to the surface, so that's got to be favorable. It's got to have enough energy, enough temperature to transverse all of the relevant activation barriers. Then the product molecules have to desorb, and then those product molecules have to diffuse out of the pore. So there's a lot of diffusion that has to go on. For the reaction to happen, all of that has to happen once the molecule gets back out, the product molecule leaves the pore, then it has to diffuse from the pore surface back through the boundary layer, and then it has to be swept away by the convection. So a lot of things have to happen in this molecule or in this reactor before before the reaction can proceed. So why am I telling you this? Number one, because it's fascinating. At least I think so. But number two, because as you can see, there are a lot of pieces to the process. So there are several steps in the process of being converted in a catalytic reactor. So those are, one, external diffusion. So reactant and product molecules through the boundary layer. We also have internal diffusion. Reactant and product molecules through the pores. We also have everything that goes on with the reaction, the catalytic reaction itself, we'll call it the mechanism, because it includes adsorption, desorption, surface reaction, activation barriers, thermodynamic limitations, etc. Everything that goes on in there. So the bottom line is that any of these steps can be the bottleneck. So So the cases we have looked at so far in this topic is the case where the catalytic reaction mechanism is the bottleneck. So we said that there was some observed experimental behavior, and so we wrote a reaction mechanism to be able to capture that. So when we say that, what we're saying is that external and internal diffusion are so rapid compared to what goes on in the catalytic mechanism that the observed rate relies only on the catalytic reaction mechanism. And then we go through and do an analysis to find out precisely what parts of the reaction mechanism are inhibiting the rate. But there are certainly cases where the observed behavior is actually being limited by internal or external diffusion. So you can think of cases where the activation barrier is very low, for example, but maybe the catalyst pellet has such a tortuous a pore network that it's hard for molecules to diffuse in and out. So in that case, molecules would diffuse very slowly. As soon as they find a catalytic particle, they react really quickly, but then it takes a long time for that particle to diffuse back out of the catalyst pellet. That is certainly a possibility. When that is the case, when a reaction is diffusion limited, meaning that the observed rate is basically the rate of diffusion of the molecules. That's what this means. So observed rate in that case, the way that we write the rate expression for our reactor design is going to be equal to a rate of diffusion. So the rate of reaction, so for example, minus our A that we're used to, is equal to the rate of diffusion. So in that case, the rate law might be equal to a rate of mass transfer times a concentration gradient. So in this case, this might be CAB, where B is for bulk, which is the concentration that would be observed in the reactor. In this case, we might say CA internal to the catalyst. So we'll say int for internal. So maybe we say here that we're going to approximate this is equal to 0. So this is a low concentration inside the particle because there's some diffusion limitation along the way. So there's diffusion is being driven by the difference in concentration, a large concentration outside of the catalyst particle, outside of the boundary layer. So in the convective flow, either in the boundary layer or inside the particle, we have a low concentration because diffusion is limiting. Hence, the bottleneck step is the rate of diffusion of the molecules to a catalyst particle. So notice that this has nothing to do with a reaction. In this case, we don't need any reaction mechanism. We don't need to know anything about the reaction orders because under these conditions, the reaction is diffusion limited. So all we need to know is how do I write a rate of mass transfer for our species, and that's how we set up our reaction rate for that case. A rule of thumb is that if you are able to measure an activation barrier of 20 kilojoules per mole or lower, usually that means diffusion limited reaction. So that's all I wanted to say about this lecture. Basically, there's a lot of processes that a molecule has to go through in order to react in a catalytic reactor. There's a lot of places along the way where that molecule could be held up. When we do reactor design, we have to be cognizant of that. Which process along the way is truly the bottleneck? If it is the surface reaction, we spent 2 lectures thinking about how to address that. But in some cases, it's not the surface reaction. In some cases, it's actually diffusion of the particles to the catalyst surface. In that case, the rate of reaction literally becomes a rate of diffusion, or at least the effective rate of reaction that we would use in our design equations becomes a rate of diffusion, because that is the thing that is controlling the rate, or that is the process that is controlling the rate.